Hi everybody. We're going to be doing section 1.7, which is modeling problems using first order differential equations. And we are not going to be doing the the circuit application. We're just going to be doing the mixing problems, okay? So let's talk a little bit about mixing problems. So what is the situation? So in these kinds of problems, we have a tank of fixed capacity containing a fluid. And the fluid is going to be well mixed with some substance. Okay? So you've got this fluid and it has some substance mixed into it, and then a fluid with a particular concentration is added to the tank at a given rate, while at the same time the well-mixed fluid leaves the tank. You know what? Instead of leaves the tank, how about I say drains from the tank? At another given rate. Okay, so this is the situation that we're going to be dealing with, and I will say that this situation if you set it up correctly, it should lead to a first order linear initial value problem, okay? So in other words, the integrating factor method that we learned will be able to be used to solve problems like this, okay? Okay, so let's go ahead and draw a picture of this, okay? Let me give you an example here. We've got our tank, and the volume in the tank, they're going to give us some initial volume, which I will call V naught. And we're going to sorry, let me back up a second here. So we've got stuff coming in, and this is dV dt, but this, let me just go ahead and call it dV dt coming in, and then coming out, we've got some dV dt going out. Okay? Okay, so then what are the steps for solving a problem like this? So as we write the steps, I'm going to be coming back and filling in this picture a little bit more. Okay, so step one. Step one, the first thing you want to do is you want to find the volume function v of t. Okay, this should not be too difficult to do because dv dt is going to equal the dv dt coming in minus the dv dt going out. And what's going to happen is this is going to be a constant. It's going to be some number. Okay? So once you get that dv dt, then you know what v of t is, right? Because if dv dt is a constant, then that means that v is going to be the integral of dv dt okay, plus c. Okay, what's that going to be? That's going to give you just dv dt times t. Remember, this is a constant, and then it's just going to be plus c, and then when you look for your v naught, you plug in 0, and this gives you that c is equal to v naught, so then that leads us to the following. V of t is just going to be whatever dv dt is times t plus v naught. This right here is the volume function. Okay. So these are the steps for the first, or this is what you do for the first step, is to find the volume function. Okay. Next thing you do, this is not your main differential equation, of course. Your main differential equation is to create a new variable. Let's say I usually use the letter a. So let's let a of t be the amount of substance at time t. So the amount of substance coming in, this is going to be the main variable that we deal with throughout this problem. And so we know that dA dt is going to be the rate at which the substance is coming in minus the rate at which the substance is coming out. Okay, so where do we get these numbers from? Remember that the concentration is given by the problem of what's coming in and also of what's coming out. So let's go back here to our picture. dA in with respect to dt is going to equal whatever the concentration is of the fluid coming in times the volume. Okay, or the rate of change of the volume coming in. Okay, now what about coming out? This is the trickier part. We know what the dV, we know what the volume is coming out, but the problem is that the concentration is actually changing all the time. Concentration is changing all the time because we're constantly pouring a new fluid in there. So this is why we can't just write down concentration coming out. So what is concentration? Concentration is defined to be the amount of substance in the tank divided by the volume in the tank. Okay? And so what we're going to multiply this by is exactly A of t divided by V of t. Okay, this is the concentration coming out, right? Because however much substance is in the tank divided by the current volume in the tank, that is exactly what the concentration is at every moment. Okay, so this is going to be what we have for our dA out. So this is our dA in, and this is our dA out, and so you have to subtract the two. And so if we come back to our page over here, this means that dA over dt is going to equal the concentration coming in times dV in over dt minus A of t over V of t times dV dt going out. Okay, it is important to note that this is going to be a constant, right? Because we are pouring in the same fluid the whole time, but this will not be a constant, okay? Not a constant. Okay. Also, this is, once you set this up right here, this is your IVP, right? What's the extra condition, of course? A of 0 is equal to A naught. Okay, so you're going to be given some initial concentration, or some initial substance amount in the tank. Okay, so finally, step 3 is to solve the first order linear IVP. And you use the integrating factor method that you learned in 1.6 to solve these problems. So of course, the setup is the tricky part for a problem like this, but once you set it up, solving it is not that difficult, okay? As long as you did your 1.6 homework first, right? So let's go ahead and do an example. A tank contains 8 liters of water, in which 32 grams of a chemical is dissolved. A solution containing 2 grams per liter of the chemical flows into the tank. Oh, sorry, containing, you know what, let me clear this up. It's not 2 grams per liter of the chemical. Let me just say 2 grams of chemical per liter of solution. This is a better way to write it. Flows into the tank at a rate of 4 liters per minute, and the well-stirred mixture flows out at a rate of 2 liters per minute. Part A, determine the amount of chemical in the tank after 20 minutes. Part B, what is the chemical concentration in the tank at that time? Okay, so we're going to start by, let's see here. I'm going to just follow the steps that I wrote down. Let's start by trying to find our volume formula, okay? This should be the easy part because it says that we're coming in at a rate of 4 liters per minute and we're coming out at a rate of 2 liters per minute. Okay, so let's write this down then. So dV in dt is 4 and dV out dt is 2. So this implies that dV dt is equal to 4 minus 2, which is 2, right? In other words, the concentration of the tank is changing at 2 liters per minute. Also, we started off with 8 liters of water, and so this means that V naught is 8. Okay, so then what would our volume function be? Well, if dV dt is equal to 2, then this means that dV is equal to 2 dt. So if we notice that we have a separable differential equation here. If we integrate both sides, we end up with V of t is equal to 2t plus c. But remember, guys, V of 0 is whatever V naught was. In this case, it was 8. So if you plug all that in here, you actually get 8 equals c. So this means that V of t is equal to 2t plus 8. Okay, we're going to need that later, right? So we're going to sort of store that aside, all right? So let's let A of t be the amount of chemical in grams after t minutes. Okay, so what is the concentration coming in? Okay, the concentration coming in, the problem did say that there was, let's go back and look. This is our concentration coming in, right? It says that 2 grams of chemical per liter is flowing in. So let's write that down. Concentration coming in is just 2. Okay, everything's in gram, liters, and minutes in this problem, okay? So this is 2. And so, since dV in dt, remember that's equal to 4, this implies that dA in is equal to 2 times 4, which is 8. Now, why did I leave a space here? Because I want to show you that the units work too, right? The concentration is 2 grams per liter, and the solution is also entering, the volume is changing at 4 liters per minute. So if you cancel those out, you get grams per minute, which is what we would expect, right? The rate at which the chemical is changing is in grams per minute. Okay, we're going to store this aside for now. Now let's talk about the out case, okay? So, remember, this is going to equal the concentration going out times dV out dt. However, the concentration going out is not a constant, right? Remember, the concentration going out is A of t divided by V of t times dV out over dt. So what is this equal to? Well, we don't know A, that's what we're looking for, so we need to leave that variable in here, A. What is V of t? Well, we found that earlier, right? V of t is 2t plus 8, so it's going to be A over 2t plus 8. And then what's the dV out over dt? Remember, that was 2. And so this is going to equal A over t plus 4. I just cancel the 2 with the 2 on the bottom. Okay, so we get A over 2 plus 4. And so we're ready to set up our IVP. Remember, our IVP is going to be dA dt is going to equal dA in minus dA out. What's dA in? It was 8 grams per minute, so it's just going to be 8 minus, and then it's going to be A over t plus 4. Also, we know that A of 0 is equal to, what's the initial concentration or the initial amount of the substance? If we look back at our problem, it says 32 grams of the chemical is dissolved. That's A naught. So this is going to be 32. So this is our IVP. We just set it up. Notice that this is first order linear, but it's not in standard form yet. So I'm going to take this term and I'm going to move it to the other side by using addition. If I do that, I get the following. dA dt plus, I'm going to write it this way, 1 over t plus 4 times A is equal to 8. And we just put it in standard form. So this guy right here is my P of x, or P of t in this case. So what is my integrating factor going to be? My integrating factor is going to be e to the integral of 1 over t plus 4 dt. This is equal to e to the ln of, I don't need absolute value because t is always positive, so it's going to be like this, but this is the same as just t plus 4. Okay? So t plus 4 is my integrating factor. Next, I'm going to multiply the whole thing by t plus 4, and so this is what we get. And on the other side, I get, should I write it as, yeah, I guess I'll just write 8t plus 32, right? How do we actually solve this? Remember, the left side actually becomes d of a times t plus 4. And on the right, I get 8t plus 32 dt. And now I'm going to integrate both sides. So on the left side, I get a times t plus 4. And on the right side, I just have to take the antiderivative of 8t plus 32. Isn't that 4t? Wait a minute. 8t plus... why did I write 3t? It should be a 32. So taking the antiderivative, I get 4t squared plus 32t, right? 4t squared plus 32t. I wrote plus c already before, so I'm just going to call this plus d. Okay, and this is a times t plus 4. Now remember, that A of 0 was equal to 32, okay? And this is our T, and this is our A, so we can use the initial condition right now. This means that we get 32 times 4 is equal to, everything's 0, and this is D. So what do we get for D? Whatever 4 times 32 is, it's 128. So D is equal to 128. So we get the following: A times T plus 4 is equal to 4T squared plus 32T plus 128. Or I could write it like this. This means that A of T is equal to 4T squared plus 32T plus 128 all over T plus 4. Okay. Now we're not done with the problem. Now we can actually answer the question though. So part A asked us how much of the chemical is in the tank after 20 minutes. Well, we could just put A of 20 in here. So if you put A of 20, we get the following. We get 4 times 400 plus 32 times 20 plus 128 all over 24. If you do all this in your calculator, you actually get 296 over 3. So this is 296 over 3 grams, right? This is how much chemical is in the tank after 20 minutes. So this is the answer to part A. Now, what about part B? Part B asks us what the concentration of the tank is after 20 minutes. So this means that we want to do A of 20 divided by V of 20, right? This is going to be the concentration after 20 minutes. What does this give us? Well, A of 20 is 296 over 3. What's V of 20? Remember, V of T was 2T plus 8. So V of 20 is 2 times 20 plus 8. What would that be? 48 on the bottom? So when you reduce this, you actually get 37 over 18. This is grams per liter, right? Because the top number is in grams and the bottom number is in liters. We're talking about amount of substance divided by the volume, right? So this is the grams per liter. This is the concentration. Okay. Now you'll notice that this, if you actually put this in your calculator, this is a little bit more than 2, right? This is 2 point something. In fact, let me put this in my calculator really quick. 37 divided by 18, 2.056. So what's going to happen is as you pour something in at 2 grams per liter, this makes sense because the concentration in the tank, the more time that passes, the more the concentration actually approaches the concentration of what you're pouring in. And if you recall, we're actually pouring in 2 grams per liter. So that's the concentration. And even though it started out as a concentration of, well, what was it? It was actually 4 grams per liter when we began because it was 32 grams in 8 liters of water. But what's happening is after 20 minutes, you've already diluted it enough for it to be almost at 2 grams per liter. Now, it'll never reach it, but asymptotically, if you take the limit as t goes to infinity, then it will reach that. So notice that if you take the limit as t goes to infinity of You know, sorry, I want to write this at the end of my problem. I'm not sure why I'm doing it here, but let's do it over here. I want you guys to notice that the limit as t goes to infinity of a of t over v of t, in other words, what does the concentration approach? Let's just calculate it for fun, okay? A of t, remember, was 4t squared plus 32t plus 128 over t plus 4. And then v of t was 2t plus 8. So when you take the limit as t goes to infinity of that, if I divide the top guy by t squared and I divide the bottom guy by t squared, I end up with the limit as t goes to infinity of 4 plus 32 over t plus 128 over t squared all over 1 plus 4 over t times 2 plus 8 over t. And that guy goes to 0, that guy goes to 0, that guy goes to 0, that guy goes to 0. You end up with 2. Which is what I was saying. So if you were to fill this thing up forever and the tank never overflowed, the concentration actually approaches what you're pouring into it, which in this case is 2 grams per liter. This is the concentration in the tank in the long run, right? This is what we mean in the long run. We're saying as infinite amount of time passes by, this is what we approach. All right, guys, I hope that demonstration made these seem not too bad. They're actually pretty simple. They always follow the same method. So just practice this application out. Thank you very much for watching.